So I wanted to discuss briefly the relationship between the density and the molar mass of an ideal gas. Do you remember this situation? A mole of ideal gas, well, helium, at standard temperature and pressure. We figured it out. It's very easy. The volume is equal to nRT over P. If that's 1 mole and that's 1 mole and that's R and that's 273.2, you get this 22.4 liters. Okay, and we've calculated that before. Now here I have a mole of methane at STP, and my point is, and we made this point before also, the ideal gas equation doesn't care that that's methane and that's helium. It's still a mole of an ideal gas at STP takes 22.4 liters. And of course, the same for oxygen. Now, all these squares are supposed to be the same size, and they're clearly not, but pretend they are. 22.4 liters for the oxygen as well. Okay, so the point is, no matter what the gas, within the ideal gas approximation, which is a very good approximation, a mole at STP occupies 22.4 liters. Okay, but then we also thought about, now what is the mass of the gas that's here? 1 mole of helium, well, that's approximately 4 grams of helium in there. 1 mole of methane, carbon is 12, hydrogen is 1, so it's approximately 16 grams. And this one, of course, 32, approximately 32 grams. Okay, so we have the same volume, but dramatically different masses. So one thing is for sure, the density changes. The density is different for these different gases. They have different molar masses, and as a result, their density is different. And moreover, it's proportional, okay? If I write the density of this, I won't actually do the calculation, but this one would be 4 over 22.4. That's in units of grams per liter. Okay, this one 16 over 22.4 grams per liter. And by the way, grams per liter, that is how we usually express the density of a gas, because gases are very light. If you use grams per milliliter like you do for liquids and solids, it'd be tiny, tiny numbers. Okay, but here 32 over 22.4 grams per liter. Okay, their density is just proportional to the molar mass, right? So here the molar mass is 4 times as big and the density is 4 times as big. Here the density is twice as big as that one. The grams of mass is twice as big and the density is twice as big because the volume is constant. So the lesson is, at a given temperature and pressure, STP, but it could be some other pair at any constant, at a given temperature and pressure, the molar mass and the density of the ideal gas are proportional to one another. The bigger the molar mass, the bigger the density. Well, there's a lesson there right away. So if somebody says, okay, here's several gases. Here's carbon dioxide, here's nitrogen gas, and here's SF6. Which of these gases at a given temperature and pressure have the greatest density? You need no further information. This has the biggest molar mass. Boom, you're done. That's the one with the biggest density at a given temperature and pressure. Just like this set here. Which one of these has the biggest density at STP or at some other temperature and pressure? Well, it would be the oxygen. Okay, well, let's get an equation that says that same thing. I just wanted, conceptually to know that the density is dependent upon the molar mass, proportional to the molar mass at a given temperature and pressure. We should be able to do that mathematically. And of course, we can't. So you have PV equals nRT as a starting point. Now listen, if I gave you some compound, I don't know, maybe some water. I gave you 13 grams of water, and I said, how many moles is that? Well, you've taken enough chemistry to know you'd have to divide by the molar mass, wouldn't you? Right? You take the mass and divide by the molar mass, and you get moles. So for instance, I'll write that down what I just said. I'll just use mass because there's too many M's and N's and stuff. I'll just say mass divided by the molar mass. And we've been using this script M for that. Gives you moles. Okay. I'll leave the S off. Okay. And you say, well, wait a minute, I'm not so sure. Well, what did I say? 13 grams of water. 13 grams of water. Just as an example of that. And let's convert that to moles. Well, I need the molar mass of water. This is the way we traditionally do it. Molar mass of water is about 18, right? 18.02. And but I need it upside down. 1 mole H2O, 18.02 grams H2O. I'll write H2O in there, okay? And that's how we get it. Grams of H2O cancel. We've been doing this since the beginning of the term, okay? But you're dividing by the molar mass, aren't you? And this is what I'm saying here. The mass divided by the molar mass gives you the moles. If we want to, we can figure out 13 divided by 18.02 is 0.72. Okay, so if I give you grams and I ask you for moles, you divide by the molar mass. Well, I can put that in this equation here, PV equals nRT. There's the N sitting there, and I could write that as mass divided by molar mass times RT, couldn't I? Right? And that's PV still. Okay. And now if you'll just permit me to rearrange a little bit, I'm trying to get a relationship with density. The density is mass per volume. I'd like a volume underneath there. So let me divide both sides. I'll multiply both sides by the M, the molar mass. And I'll divide both sides by the V. So P, still there, multiply by M, mass, still there, divided by volume, times RT. Okay? And then this, well, that's what I wanted, right? That is the density, isn't it? Mass divided by volume. We got to be careful, make sure, usually we're using liters for this, and then the molar mass, we're usually, if that could be grams, we should use grams for the mass and liters for that. We'd have grams per liter. We'd have density in grams per liter. I'll write that down here. I'll put in parentheses, grams per liter. But that's our D. That's our density. DRT. So we got a nice little equation there. I'll rearrange it just a little bit more. I don't know, do we want an equation that says D equals something or M equals something? I'll tell you what, let's go for D and we'll divide R by RT. So we'll have the density, and remember expressed in grams per liter, is equal to P, this script M over RT. And by the way, notice that this embodies what we said before. We said that the density and the molar mass are proportional at a given temperature and pressure. Well, look, here's temperature and pressure and R. That's, if you hold those constant, density and molar mass are proportional to each other, okay? So we've got a nice little equation for the density. We could also rearrange this. I could multiply both sides by RT and divide by P. If you want another version of this, it would be that the molar mass is DRT over P. And you could stop the video and prove that to yourself if you'd like. But we have these two versions of the same thing. There's not really a lot of new information here. This is just the ideal gas equation, and perhaps casting it in a slightly different form. Now, we have some problems to practice with. Let me share those. If I can remember how. So, okay, share and share what? Share this. Okay, so I've got some problems here. I'm gonna, while you're reading that, I'm going to write some of the material on the board that we need for that. That first problem we'll look at, let's see, it's find the density from the molar mass. Oh, okay. Well, I think I know which equation I want. What is the density of carbon dioxide gas at STP in grams per liter? Oh, well, that's easy because I happen to know the molar mass of carbon dioxide, don't you? 44.01, right? So if it's, we'll use this one because it asks for density. And then what was it? It's P times the molar mass over RT. All right, and they asked about STP, and I know the molar mass for carbon dioxide. It's 44.01 grams per mole. So let's put in all the units and make sure this works out right. STP, so P is 1 atmosphere. Okay, now my molar mass, 44.01 grams per mole. That's for carbon dioxide. You can check it out if you want. Take my word for it. Okay. R, 0.08206 liter atmospheres per mole Kelvin, all of that. And then the temperature, we're at STP, so that's 273.2. So checking our units here, let's see. We have atmospheres in the numerator and in the numerator of the denominator, so we can kill those. Here's kelvins, those go away for sure. Moles in the denominator of the numerator and the denominator of the denominator, so you can kill those. And look what's left, grams and liters, which is what we want, grams per liter, right? So, okay, let's do the math. It's 44.01 divided by 0.08206 and divided by 273.2 equals 1.96 and grams per liter, because it's the density. It's just exactly what we want. So hopefully that is actually what is on that sheet. I noticed it had the answers on it. Let's look there for another problem anyway, because that was an easy one, right? I hope. Let's see. Here we go. Yeah, 1.96 grams per liter. So we got it right. Now, number 2 is kind of similar. Find the density from the molar mass. What is the density of carbon dioxide gas? It's a different temperature expressed in centigrade and a different pressure expressed in kilopascals. Okay. But in principle, not a very different problem at all, just some unit conversions you have to do there. So I'm going to leave that up to you. You should be able to get the 2.09 grams per liter out of that. You do some conversions and do exactly what we just did in problem 1. How about this one? It's the other way around. Find the molar mass from density and temperature pressure. A forensic scientist. Okay, let me write some of this stuff on the board. Oh boy, I've got my computer's objecting to something here. Okay, hopefully that will go away. I've been getting that popping up quite a bit. Okay, a forensic scientist adds 0.2011 grams of an unknown gas to a well, I almost gave it away, 125 milliliters. That would be 0.125 liters, right? But look, they're giving you the mass and the volume. They just gave you the density, right? And the pressure, 736 torr, and the temperature, 20 degrees. Is the gas likely to be which? Well, we can find the molar mass, and then we'll be able to figure out which of these it might be. So let me write some of this information on the board here. While you're looking at the rest of that, it's 0.2011 grams. The flask is 0.125 liters, if you don't mind me doing that conversion in my head. Then it's 736 torr and 20 degrees, 20 degrees. Okay, and let me go back to the blackboard. Here we go. Okay, so, and this time we're asked for the molar mass, right? We want to find which of those gases it was. So molar mass, how did it go? dRT over P was our equation. And I don't know how we want to do. Want to plug all that stuff in there, or do you want to do a little preparatory work here? Let's find out our density. Density, because they gave us a mass and a volume, were there. 0.2011 grams divided by 0.125 liters. And let me figure out what that is. And it's an intermediate result, so I want to carry along probably an extra digit to make this turn out right. But 0.2011 divided by 0.125 is, I get 1.60, I'll call it 1.609. It's actually 1.6088. And what are my units? Grams per liter. That's what we want for the density of a gas. Okay. And, you know, it's really only 3 significant figures there, but I'm carrying along an extra one. Maybe I should write that 9 small or something so that I remember that. But anyway, 736 torr, now that's almost, let's see what that is, divided by 760, right? You know how to do these. If you take torr and divide it by 760, you get atmospheres. It's 0.9684 atmospheres. Okay, and then 20 degrees C, 20.0. So that would be 293.2 Kelvins. And you do have to use Kelvins, you know that, right? Yeah, definitely, definitely. And now with that, I think we're ready to do, we can very quickly, because I run out of room on this board, but the density 1.609 grams per liter. And yeah, I'm going to run out of room. I'll write really small. You know what I'm writing though, 0.08206. And it's liter atmospheres per mole Kelvins. And then 293.2 K. I'll write it sideways. 293.2 K. So stay with me on here. Write this out nice and pretty on your page, because I'm kind of going up the side of the board. And then what's the pressure? 0.968 atmospheres. I can write that big. Okay. Oh yeah, check our units. Let's make sure the units cancel out properly. Now this, look, there's liters in R. It's 0.08206 liter atmospheres. So the liters there cancel those liters there. Atmospheres in the numerator of R there and in the numerator of the denominator, or in the denominator, Kelvins cancel, and I have what's left, grams per mole, a molar mass. That's what it's supposed to be, isn't it? So let's see, how does this go? 1.609 times R, 0.08206, times T, 293.2, and divided by the pressure, 0.9684 equals, it says it's 39.975. 39 point, look, it's 0.9 and then 75. We, if we round that to three significant figures, which is what we should do because we have 3 there and 3 there. So it's 40, okay? It's 40.0 grams per liter. Oh, grams per mole, I'm sorry. This is the molar mass we're calculating. Grams per mole, 40.0 grams per mole. Which of those gases has a molar mass of 40.0 grams per mole? Let's see. Methane would be 16, nitrogen's 28, oxygen's 32, neon's about 20, and argon 40. 40, that is the molar mass of argon. So we got that one, I think. Okay, let's look at this next one. Then this is a little more interesting now, okay? Well, there's a typo. Density and molar mass are proportional at a given temperature and pressure. That's sort of our overriding lesson today, isn't it? At a given temperature and pressure, the density and the molar mass are proportional. But you notice in this problem, I guess I should let you read it. It's not giving you a temperature and a pressure. It just says, under the experimental condition, right? A chemist found the density of Freon 11. They give you the molar mass, 137.37, to be 5.58 grams per liter under her experimental conditions. Now that would be temperature and pressure, but they didn't say what they are. Her measurements showed that the density of an unknown gas was 4.38 grams per liter under the same conditions. So they're saying the same temperature and pressure. So what was the molar mass of the unknown? How are we going to tackle that? Let's look at this equation a little bit, and then we'll see, I think. It's targeting the fact that they're proportional. The density and the molar mass are proportional. So here's that same equation that we used before. D equals, and then it's P over RT. I'll write them separately. P over RT times the molar mass, okay? This is proportional to that at a given pressure and temperature, okay? That's the point. This is the constant of proportionality, because for these, if we say we're going to hold a certain pressure and temperature for these two measurements on these gases, or like the ones that I had on the board at the beginning where we said they were all at standard temperature and pressure, we're holding this ratio constant. It's like the constant of proportionality, and the density and the molar mass are proportional. Now, so you could just write for this problem anyway, density, proportionality sign, right? Looks like a fish, okay? Density is proportional to molar mass. So if that's the case, then the ratio of two densities in the two measurements that this person made, the ratio of the two densities ought to be equal to the ratio of the two molar masses. Let's call, let's see, one of them is Freon, CFCl3, and the other is an unknown. We'll call it X. So let me just say, let me ask you about this ratio, dx divided by dCl3. FCl3. You have to look and see what that is. That's the freon. Okay. And we just, if you don't believe what I was saying, that it's the rate, that this ratio would be the ratio of the molar masses, go ahead and plug in our equation. Okay. It's P over RT times the M for the X, for the unknown. And it's P over RT for the molar mass CFCl3. Okay. But the deal was that both the measurements are made at the same pressure and temperature. So this P over RT up here cancels the P over RT there. And all you really have is the molar mass of X and the molar mass of CFCl3. Okay. So that's the equation I want. Get this junk out of the middle. This is what I'd like, right? These two ratios are the same because those quantities are proportional. All right. I'll tell you what, let me clean this up a little bit. I'll just move my molar masses over. But dx is molar mass of X, CFCl3. Okay, so we want, in this case, we want the molar, they gave us the density of the unknown. What was that? That was 4.38 grams per liter. This one, we know 5.58, and the molar mass of the freon was 137.7, and this is what we want to solve for. So I'm just going to multiply both sides by that molar mass of the freon, and I should be done. So molar mass of X equals the molar mass of the freon, CFCl3, times this ratio, dx dCFCl3. And that in turn, it's 137.37. 137.37 grams per mole. And now the ratio of the densities, they got the same units. The units are going to cancel out. The units on the density of the unknown is 4.38 grams per liter, and the other is 5.58 grams per liter. And like I say, you can push grams per liter down here twice and then cancel them out. And we're done because, let's see, 137.37 times 4.38 divided by 5.58 is 107.8. How many significant? Well, we've only got 3 significant figures in these, so we can only do, I have 107.8 on my calculator, but it's 108. Significant figures wise, it's 108 grams per mole. So hopefully that matches the answer on the sheet. It does. So we're good with that. So I just wanted to present that equation, remember what it's about, and do a few examples. And now up to you to do a little homework on it. So I'll let you get to it. But thank you, and I'll leave it there. Thanks.